All right. Hello, everyone, and welcome to our presentation. Today, we are going to be talking to you about the tools that we developed for LEAP to help to further their mission, which is to increase the efficiency of homes in Charlottesville. Just a little bit of background on LEAP. That stands for the Local Energy Alliance Program, and again, they're just a local nonprofit that was founded to help increase the efficiency of using both energy and water in the local community, and also to increase the education about that. So we attacked this problem of developing the tools from 3 different angles. The first one was monitoring,
which was done by me. My name is Joshua Scott. Research shows us that monitoring real-time energy usage, homeowners can be able to change their energy use. The other flip side of that, however, is being able to display that data so they can understand it. So it can get fairly technical. So the other side, what we did was, through the help of the affiliated course, we created a display that's always up in ecoREMOD so that patrons of ecoREMOD can see it, and that also the workers with LEAP can also see their data.
With modeling and simulation, we're looking at increasing our knowledge of Energy Plus, a modeling system, so that we can actually use it to model energy usage for houses and predict what retrofits would be most effective to decrease their energy usage.
And then finally, the third tool was to develop an automated window blind system. The goal of that was just to take advantage of the various energy flows that are going in and out of the building, just to help increase the efficiency and decrease consumption. So we'll first get started with monitoring.
Okay. So in ecoREMOD, we're measuring a number of different things. Thank you. We're measuring temperature, humidity, carbon dioxide, and electricity. And so what we've used is a company called Onset, which is here. This is basically a data node that's able to take in a myriad of different sensors. They can be created right here on campus, or they can just be bought off the shelf. We've gone with bought off the shelf. And basically, this sends data to a wireless computer that's located upstairs. So basically, we're able to give us a lot of flexibility to have a lot of sensors, but not a lot of wires. This over here is a carbon dioxide sensor. Just an example of what a sensor may look like. This device measures carbon dioxide and temperature. We would want to see carbon dioxide data, for example, to see how well the heating, ventilation, and air conditioning unit is working. If the CO2 levels are really high, it could mean that the HVAC system is not circulating enough air from the outside. And so just to give an example of the things that we can do with the temperatures, or rather the data that we collect, it gives us a lot of wiggle room and a lot of manipulation of what we want to present to homeowners that want to work with LEAP. So what I pulled right here is temperature data from March 4th and March 6th, or through March 6th. If you guys remember, it's the first day of spring break here. We had a snow, and then all of a sudden it disappeared by like 2 p.m. the next day. And I apologize for not having any axes, but yeah. But anyway, so the first thing we can look at is the stud and insulation temperature. We were given the opportunity to see the whole renovation of this home. So what we were able to do is put temperature sensors directly into the foam insulation, and then also next to 3x4 stud or 3x2 studs that are in the walls to see how well the insulation is doing. If you take a look at the data here, and also, I don't have the spreadsheet, but there's generally a 2 degree difference all year round. We've had this installed since April of last year. And so that's a good indicator that there's not a lot of heat loss between the insulation. Next, if you add the indoor temperature here, this shows that the HVAC system is doing fairly well. It's keeping the indoor temperature steady at 70 degrees during that time of the year. And then you would add in the outdoor temperature, which fluctuated a lot that day because of the snow. So here it gets pretty close to freezing. However, the indoor temperature stays pretty steady at 70 degrees, while the insulation temperature and stud temperature kind of follows the outdoor temperature, but not so much that it's that cold on the inside. The other side I said to monitoring is being able to display that data. So through the funds that we were able to receive with JPC, we purchased a 42-inch TV that LEAP can use for presentations and also to display their data and events. So down here, are some data points that we have, and this is just the beginning. We can add more things when we can. These circulate every 10 minutes. Here are events. Here we can circulate graphs and other pictures of the renovation, and customers can go to LEAP resources here through their website.
Okay, so there are three main areas of home energy consumption. They're lighting, heating and cooling equipment, and large appliances. And the degree to which each contributes to a home's energy use is largely dependent on the occupant behavior, in addition to just the condition of the appliances and their age. And these three areas of home energy consumption were three of the main input variables into Energy Plus, which is a free software program provided by the Department of Energy, which enables users to put in various data attributes for each home building aspect, such as insulation properties, heating and cooling equipment, and lighting. And the output is a simulation that simulates the amount of energy that the home will consume. And it's a tool for LEAP because it allows them to simulate potential energy savings with home upgrades in place. Speaking about some of these inputs, particularly heating and cooling equipment, basically old equipment is very inefficient compared to new equipment, obviously. And one benefit new equipment has is that from a comfort standpoint, given the greater technology, there are ways to improve homeowner comfort with multi-stage heating and cooling and further dehumidification capabilities. And these are all elements that would impact a homeowner's decision to upgrade, not just the return on investment. Lighting, you have older incandescent lights compared to newer fluorescent lights, which consume less wattage for the same amount of light output. So upgrading to more efficient lighting is one way to modify simulation results to lower energy costs. Lastly, you have just the occupant behavior. You look at a home up to the top corner, looks like it's hardly ever occupied, versus a home that seems to be occupied 24/7 with lights left on and TVs left on. Occupant behavior is a major component to home energy use, and so simulating the occupancy schedule is one of the ways we can consider ways to save energy. And from that aspect also, you look at an older home, the building envelope will be considerably less tight, meaning the building is more leaky and has less insulation, which causes more energy usage.
All right, this is ecoREMOD 1. It's one of ecoREMOD's Sustainable Housing Initiative proof of concept houses. They've been built to show what the current technology can do and to help bring the technology further forward. This is an Energy Plus model seen in Google SketchUp. This is one of the inputs into the Energy Plus model, which is the geometric model. And as you can see, they look very similar. So using this modeling program, we've looked at the HVAC energy usage. And as you can see, the simulated is in orange and the blue is the monitored. And we've actually gotten it to be a fairly close fit. But of course, there are imperfections in our model. Part of it is because of the leakiness of the house, which we have not necessarily gotten into the model correctly. Also, there are electric loads, which we haven't fully accounted for, and random thermostat settings, which we'll get to here. As you can see, in April and in March, the monitored settings are much more varied than the simulated settings. The simulated settings were set to be between 71 and 74 degrees Fahrenheit. And of course, people will turn off their thermostat or change their thermostat setting, which will cause that variation and problems with the model. So this tool is meant to be a tool to help with an informed decision so that a homeowner can consider their comfort, look at their budget, make an informed decision about what retrofits would be most appropriate for an investment to increase their comfort.
Okay, and so the final tool that we developed was an automated window blind system. And the basic problem that this system is meant to address is just that there's a lot of uncontrolled energy flow happening in a building. As you can see here, there's heat transferring in by conduction through the floor, the ceiling, the walls, but most significantly through the window, just because windows have a higher thermal conductivity. Another significant form of heat transfer is just due to the sunlight. So what's the way that most people deal with this? They put a drape in, and that drape limits that thermal heat flow, both due to conduction and radiation. But that's very inefficient because humans are largely unaware of all of the data that is available to them about temperature and sunlight. And so what we did is develop a mechatronic system which basically interprets data from the environment, puts it into a microprocessor, and then sends a signal to a motor which moves that drape up or down and optimizes that heat flow. We don't have too much time to go into detail, but this is a basic show what the algorithm looks like inside that microprocessor, and then here's an image of a part of our circuit. So that's all we have time for, but we'll definitely take questions at the end of the session. Thank you.